Section 8.4, molecular shapes. The objectives of this are to summarize the VSEPR bonding theory, predict the shape of and the bond angles in a molecule, and define hybridization. Some vocabulary you're going to want to review is atomic orbital, and some new vocabulary you'll come across is VSEPR, model, and hybridization. The shape of a molecule determines many of its physical and chemical properties. Often, shapes of reactant molecules determine whether or not they get close enough to react. Electron densities created by the overlap of the orbitals of shared electrons determine molecular shape. Theories have been developed to explain the overlap of bonding orbitals and can be used to predict the shape of the molecules. The molecular geometry or shape of a molecule can be determined once a Lewis structure is drawn. And this is why I like the Lewis structure over the structural formula. The Lewis structure tells us the geometry. The model used to determine the molecular shape is referred to as the valence shell electron pair repulsion model, or you'll hear me refer to as VSEPR. This model is based on arrangement that minimizes the repulsion of shared and unshared electron pairs around the central atom. To understand VSEPR model better, imagine balloons that are inflated to similar sizes and tied together as shown in figure 818. Each balloon represents an electron-dense region. The repulsive forces of this electron-dense region keeps other electrons from entering this space. When a set of balloons is connected at a central point, which represents a central atom, the balloons naturally form a shape that minimizes the interaction between these balloons. The electron pairs in a molecule repel one another in a similar way. These forces cause the atoms in a molecule to be positioned at fixed angles relative to one another. The angle formed by two terminal atoms and the central atom is a bond angle. Bond angles predicted by VSEPR are supported by experimental evidence. Unshared pairs of electrons are also important in determining the shape of the molecule. These electrons occupy a slightly larger orbital than shared electrons. Therefore, shared bonding orbitals are pushed together by unshared pairs. The shapes of food molecules is important to our sense of taste. The surface on your tongue is covered with taste buds, each which contain 50 to 100 taste receptor cells. Each taste receptor cells can detect 5 distinct tastes: sweet, bitter, salty, sour, and umami. Right? Umami is like that savory flavor, right? That kind of makes you go, mmm. But each receptor cell responds best to only one taste. The shapes of food molecules are determined by their chemical structures. When a molecule enters a taste bud, it must have the correct shape for the nerve in each receptor cell to respond and send messages to the brain. The brain then interprets the messages as a certain taste. When such molecules bind to a sweet receptor, they are sensed as sweet. The greater the number of food molecules that fit a sweet receptor cell, the sweeter the food tastes. Sugar and artificial sweeteners are not the only sweet molecules. Some proteins found in fruits are also sweet molecules. A hybrid occurs when two things are combined and the result has characteristics of both. For example, a hybrid automobile uses both gas and electricity as an energy source. During chemical bonding, different atomic orbitals undergo hybridization. To understand this, consider the bonding involved in the methane molecule. The carbon atom has 4 valence electrons with the electron configuration helium 4s2 2p2. You might expect the 2 unpaired p electrons to bond with other atoms and the 2 s electrons to remain unshared pairs. However, carbon atoms undergo undergo hybridization, a process in which atomic orbitals mix and form new identical hybrid orbitals. The hybrid orbitals in a carbon atom are shown in 819, right over here to the left. Note that each hybrid orbital contains one electron that it can share with another atom. The hybrid orbital is called sp3 orbital because the 4 hybrid orbitals form from one s orbital and 3 p orbitals. Carbon is the most common element that undergoes hybridization. The number of atomic orbitals that mix and form the hybrid orbital equals the total number of pair of electrons. In addition, the number of hybrid orbitals formed equals the number of atomic orbitals mixed. For example, aluminum trichloride has a total of 3 pairs of electrons, and VSEPR predicts a trigonal planar molecular shape. This shape results when 1 s and 2 p orbitals on the central atom aluminum mix and form with 3 identical sp2 hybrid orbitals. Lone pairs also occupy hybrid orbitals. Compare the hybrid orbitals of beryllium chloride and dihydrogen monoxide. Both compounds contain 2 atoms. Why does dihydrogen monoxide molecules contain sp3 orbitals? Since there are 2 lone pairs on the central atom, on the oxygen central atom in H2O. Therefore, there must be 4 hybrid orbitals, 2 for bonding and 2 for lone pairs. Recall from 8.1 that multiple covalent bonds consist of 1 sigma bond and 1 or more pi bond. Only the 2 electrons in the sigma bond occupy hybrid orbitals such as sp and sp2. The remaining unhybridized p orbitals overlap to form pi bonds. It is important to note that single, double, and triple covalent bonds contain 1 hybrid orbital. Thus, carbon dioxide with 2 double bonds forms sp hybrid orbitals. Okay. So here is a chart to kind of give you an idea of what shape a molecule may take. Ask yourself about the central atom. It's always going to be about the central atom, right? The terminal atoms really don't apply in this shape just yet. But it's always going to be questions about the central atom, right? How many total pairs exist about the central atom? How many shared pairs exist about the central atom? And how many lone pairs of electrons, right? How many lone pairs exist on the central atom? And this would kind of give you the hybrid orbital shape. And this over here will then go ahead and tell us the molecular shape. Right? So there are quite a few different shapes: linear, trigonal planar, tetrahedral, trigonal pyramidal, bent, trigonal bipyramidal, and octahedral. And if we're looking at this, we have these little purple lobes. These purple lobes represent lone pairs of electrons. And again, these the ball and stick represent a terminal atom and the bond that it has about the central atom. So let's go ahead and do an example. Phosphorus trihydride, a colorless gas, is produced when organic materials such as fish flesh rot. What is the shape of phosphorus trihydride molecule? Let's go ahead and identify the bond angle and size of the hybrid orbital. So we're going to go ahead and create the Lewis structure, right? Pretty familiar with that from last section. So when you're doing this, right, find out how many pairs, and then you go ahead and put them around and find out your lone pairs. And when doing this, right, we can go ahead and create the Lewis structure. We see that about the central atom, it has 3 bonding pairs and 1 lone pair. So if we kind of go ahead and look at that chart above, what has 3 bonding pairs and 1 lone pair? It must have a trigonal pyramidal shape and a bond angle of 107.3. So how about you go ahead and pause the video and give these 4 a try. Right, 56, 57, 58, and 59. So here's the work for those problems, right, I like to go ahead and label out how many total pairs, how many shared pairs, how many lone pairs, right? And that would go ahead and tell me, well, what's the shape of this molecule that I'm dealing with. All right, section summary. VSEPR model theory states that electron pairs repel each other and determine both the shape of and bond angles in a molecule. Hybridization explains the observed shape of molecules by the presence of equivalent hybrid orbitals.